I know many of you are looking forward to listen to the CPC, but before I do that, I want to talk actually another project, which is the foundation of a CPC. So this really lays the idea for CPC. So this is called a standard. So that's why I put, it's not only myself there. It's actually on behalf of standard team. So it's really say, I want to talk about why we use network complexity and why spatial temporal data mining there, which really shows in the standard project, and why we need to do CPC. So that's the future direction actually defined by that. So there are many definitions about lateral complexity. If you go to the website, actually there's one website dedicated to what is lateral complexity definition. They start from structure to management to operation, and then they add more things on, say, what's the impact of other activities and the lateral complexity. So make it a very complicated diagram, which I don't dare to show you here. But I think fundamentally, the lateral complexity really comes three things, I think, okay. So you may not completely agree with it, but I think that's a fundamental issue here. Actually, we've already had a lot today already. The first one is the heterogeneity. It's really reflected on the structure and the performance. So it's non-linear and also, and also non-stationarity. One stationarity has been talked a lot in GI science. It's the multivariable area unit problem. I know some of the audience knows that. I personally think actually we have great progress in terms of discussing about the structure. We talk about the power laws, you know. It's very good in talking about what it is, but how we're really able to model and predict non-linear or stationary performance, actually, how to talk about this global and local phenomena is quite difficult. There are some, that's what actually we are working on that. And another thing, fundamentally, everything is dynamic. So what it really means dynamic really means actually we're changing structure. So we're changing load, changing link. Can be you have more people using the internet now, we got more loads. So that really imply for the change in supply or capacity. Another thing, the movement and the network definitely keep on changing all the time. Morning peak, evening peak. So the density, flow, speed. But the most important, actually, the behavior. Actually, we'll talk more a little bit later on, and we'll talk more about what's the influence of behavior and the network. Even everything is the same. And actually, that leads to the change in demand. So as we can say, with a lot of progress in modeling the supply and demand at the global or macro level. But what really the implication, as I said already, for the behavior, especially what's their connective effect on the network, is a little bit missing. And also there's no readily tools really able to demonstrate or to capture the transition from free flow to congestion. And thirdly, we talked about already, the previous one, interaction and association. So what it really means, people talk about spatial, temporal, and also actually we really need to look at integrated spatial temporal and of course multiple factors and multiple networks as well. So that's what I'm trying to say. We need really integrated treatment of spatial and temporal together simultaneously and seamlessly. And also, we need to think about multiple networks. That's the previous talk still gave already. So based on that, I would say that's what we focus on. I'm trying to put everything. What I'm doing is important. That's why I said the research frontiers. But it's really the things we really need to look at it. Actually, that's the thing. Actually, we really look at the things in standard project. So we really look at, say, if we're able to provide some model to do the forecasting and the prediction based on the nonlinearity and the non-stationarity of the data. And most importantly, we really would like to capture or to demonstrate the process to get the emerging pattern or capture the tipping point. So before the things are getting really, really bad, as the virus hasn't been fully spread out the real network, can we say, do something, stop them, or migrate them? And we'll talk more on that, simulated behavior. And in terms of the spatial temporal dependence and the interaction, we really want to look at what's the impact of the activities on the network and also to know the interactions. Of course, everyone talk about big data. You already heard about the data a lot already today. The data travel showed this morning what the data we got, and also GPS data we got for the policeman vehicle. As far as if my memory right, for 1 month's Camden data, only for the vehicle we got 70 megabyte, only for the GPS police vehicles. For actually only 4 vehicles for 1 borough in London. Okay, that's the data we're talking about. So similar for transport. So for the standard project, we actually provide a very good platform to study lateral complexity, which we're putting together as several things we are looking for. Really try to understand the traffic congestion in central London in space and in time. So we really want to look at, can we make short-term and longer-term journey time prediction? And can we really detect the traffic congestion as early as possible? And also, we actually want to provide a tool to really able to interactively visualize the journey time. And we really wanted to, if something happened, is long-planned congestion, what we should do? Can we simulate it, but provide a better traffic migration if possible? And of course, we also do intervention analysis. I'm not going to talk about that because that's kind of a conventional transport analysis. We'll look at this full aspect by showing some examples in standard. So, I said it's spatial temporal data mining. So why is linked up to spatial temporal data mining? Actually, that's all the method we're using here is from there. So in terms of spatial temporal data mining, actually, John also mentioned about some machine learning is quite relevant. So the 2 approaches, statistical approach and a machine learning approach. We will say, for statistical approach, it's good to understand the factors, but how to calibrate the spatial temporal autocorrelation is a bottleneck. But for machine learning approach, it's a very good non-parametric approach, but the interpretability of machine learning is relatively low. So actually, that's the limit we have. So if you look at the example, everyone must know this. Google, very good. When you go on somewhere, check the map, tell you the location, tell you the navigation, the directions. And also now, you can even check the real-time traffic. You want to look at the real-time or you want to look at the historic data. I'm not sure if anyone have ever checked or really believe how accurate the data are. If I ask my colleagues in TFL, they will say, okay? But what we're trying to do is say, we're trying to say, if possible, can we do something a little bit even better? So the strategy we're doing here, as I said, the fundamental issue is the spatial temporal autocorrelation. And fundamentally, it's the dynamics and the locability of your data. So we developed a model able to accommodate in the autocorrelation locally and dynamically in the model. So this is really give you some just very quick examples. And what we produce is really say we have a relatively good accuracy in terms of prediction. This is actually still statistical approach. Later on, James, in a few minutes, he will talk about using canon-based approach, machine learning approach to do the prediction. Another one is the clustering. As I said, really clustering is a K2. We're able to extract some meaningful patterns, especially we want to look at the emerging one. As I said, really how we are able to really consider the process in it is a key issue. There's some good tools coming. But it started from spatial scan statistics to space-time scan statistics. So, but the computational efficiency is still, it basically is very computational intensive. How to improve the efficiency is a challenge. So here is an example. Basically, we're trying to show is any some pattern. You can see it. So this is the day. The state opening, the parliament's opening. So you can see that actually the traffic really started from this link, but keep on, propagated to the adjacent links. So in this way, we're able to attract some. This is really talk about long recurrent congestion. We know like Gower Street every morning is busy. We're not really interested in it because it's in your perception already. What we're looking for is something not in your perception, not in your plan. So that's something really to pay attention to. So visualization, you already say a lot already. Let's just move on. So this is nothing new here. Basically, this gives you a kind of hotspot map. Same for crime as well. We put it in a 3 dimension. This one can help you say how you change. This is a tube strike, if you remember, last year. Started from 9 p.m., finished at 9 p.m. next day. So you can see the pattern very different. Nothing new still. This is another way. Isosurface, Chris just talked about as well. So you can see the range in terms of space and time very different for those 2 days. This is still a lot of very interesting because we really want to use some dynamic interactive tools. So this one can help you say, image is very straightforward because large amount of data is quite difficult. Most difficult thing actually is the next slides will show you to. So basically this one can really let you say the conjunction is built up. So if I move to the next one, this is now just ready to run the three-dimension models is quite difficult. The technology is available, but it's how to improve the speed because of the density of data. So really, that's one give you an overview of the whole network. If you really want to just say one link, can give you some tools to do that. We unfortunately couldn't show you the visualization we developed for the Olympic Games. TfL provided some routes to let them to simulate the possible journey time reliability, but we're not allowed to show you. But anyhow, give you a flavor. So next one is really the final one. Is the simulation, agent-based simulation. I think later on our keynotes we are talking more on that. So this is really say how we really can understand the formulation of a conjunction based through the behavior of individuals. And actually we take a multi-scale approach. It starts from individual driver and the individual links come to the junction and come to the whole network. Give a flavor on that. So this is the, Ed going to talk more on that as well. This is really, we're trying to use 3,000 agents to run around in this area. And this 30,000 agents. These 30,000 agents, they can be taxi driver, they can be commuters, they can be tourists. That means they have different spatial knowledge of the region and also they have different preference of the route choice. So you can say that if it's getting congested, basically the color going to change. I think I'll leave Ed to show more later on. Okay, just the flavor there. Okay, so there's another one. Nearly there. So this one, now we've all got a smartphone, GPS data. You already see some different GPS data already. This is not PhD research with Adele. So this is the one really say, that's the right dot basically is your GPS track. So what you can really get from that to understand the behavior. So this is the code we translated into travel mode. And that's what we want. So I move to next one because we have 100 participants. This one, everyone got 2 months data. If I let it run, it come to tomorrow. So to make it simple to say the final result. So this is really the one we're putting together. That's 20, basically it's 20 participants data. Can you really guess what is that? So show a little bit something out. If I show the next one. So where is this?
UCL.
Yeah, why is UCL? Because the first 20 participants basically choose from UCL, the friends of Adele, okay? but somehow you can say that the pattern is really kind of can show up and also some hotspot area will come out. Let's give you a flavor. So really to summarize, the many things we can do in future if I link up lateral complexity with spatial temporal data mining, I think. Now we got more cloud source, so we have to combine them because I'm a person who knows a lot about the space. So actually I don't know much about text mining. Might be useful when you talk about social networks. And especially, that's the one I try to emphasize. When we have networks, really want to emphasize on the interaction and the dynamic flows because that's the process behind it. And also, emerging patterns, the tipping point is still the key issue we would like to look at. And another thing is we find some pattern, how we calibrate it is really true. We have social media, so many data. Yeah, we find some pattern. But actually, we need the calibration and explanation. That's why we need domain experts. So that's the one I put in there. Many other things here, but the key issue, we need more systematic application. So that's why we need the CPC. We need the interaction of different networks. That's something I'm going to talk in about our time. Thank you very much for your attention.